You ever just look around and think about how dramatically different the places on our planet are?
Oh,
We've
absolutely.
got these immense mountain ranges jutting into the sky, then these sprawling oceans that feel endless, and deserts sculpted by winds that go on for miles.
Yeah, and each one has this distinct feeling, doesn't it? Whether it's awe or maybe even a sense of, our own smallness in the face of it all.
Totally. It
Yeah.
really makes you wonder, what are the forces that actually created these incredible landscapes?
Well, that's the exact starting point for geologists when they look at any landscape. It's not just about how pretty it is,
Right.
but about deciphering the story etched into the Earth's surface. How did this particular configuration of hills and valleys, coastlines and plains come to be?
And how will it change?
And what are the ongoing processes that will continue to shape it in the future? Yeah, that's the core mystery we're exploring today.
Right. So in this deep dive, we're setting out to really understand the fundamental engines driving landscape development. We'll be digging into the key processes that sculpt our planet's surface. And a huge part of that story is the constant movement of water, the hydrologic cycle.
That's critical.
Getting a solid grasp of these basics will be so important when we later start looking at specific landforms like canyons, cliffs, and beaches, and understanding their origins.
And to frame our discussion, it's crucial to recognize that the Earth's surface is in a constant state of flux, shaped by two opposing but interconnected sets of forces.
Okay.
On one side, we have uplift and subsidence, the vertical movements that raise and lower portions of the crust.
Up and down.
Exactly. On the other side, we have erosion and deposition, the wearing away and accumulation of surface materials.
Breaking down and building up.
Right. And then permeating all of this is the hydrologic cycle, the continuous circulation of water that acts as a primary agent in those erosional and depositional processes.
Got it. And you mentioned we'll look at other planets too.
We will, yeah. Just to give us a broader context, we'll even take a quick look at some landscapes on other planets and see how they compare, give some perspective.
Okay, let's get into it. It's easy to take mountains for granted, but what fundamental forces broke the mold of a potentially featureless early Earth? You mentioned uplift and subsidence. Can you explain what those are all about?
Absolutely. Without these up and down movements of the Earth's crust, the dramatic variations in elevation we see, the mountains, the valleys, the plateaus, simply wouldn't exist.
Flat Earth otherwise.
Pretty much, yeah. Uplift, in essence, is the relative upward movement of a part of the Earth's surface compared to its surroundings. Think of the Rockies rising.
Okay.
Subsidence is the opposite, the relative downward movement, like the Mississippi Delta slowly sinking.
Ah.
Now, what's fascinating is the diverse range of geological activities that can trigger these movements.
Yeah, our sources have table F.1, which lays some of this out. For uplift, we see things like the crust thickening.
Right, like when tectonic plates collide.
Exactly. India hitting Asia, creating the Himalayas. That's still happening, right? Pushing them up.
It is, absolutely. Or the heating of the lithosphere, which makes it less dense and more buoyant, causing it to float higher on the underlying asthenosphere.
And then there's rebound, like the Earth slowly springing back up after a massive weight, like a mile-thick ice sheet, melts away.
That's a great analogy, like a mattress regaining its shape after you stand up.
Yeah.
And then there's something called delamination. Imagine a dense layer at the bottom sinking away.
Huh.
The lighter stuff above then bobs up. So when a dense part of the Earth mantle detaches and sinks, the lighter crust above rises.
Wow. Okay, and on the subsidence side, what makes things go down?
Well, the crust thinning is one cause, like when it's being pulled apart, such
Mhm.
as in the East African Rift Valley.
Okay.
Cooling of the lithosphere also causes it to become denser and sink. And finally, the opposite of rebound. Sinking due to loading. Yeah, where the immense weight of something like a massive volcano or a huge pile of sediment just pushes the surface down, like that mattress again when you step on it.
Gotcha. So these vertical movements create what we call topography, right? The variations in the land's elevation.
Correct.
And how do geologists actually represent this three-dimensional information on a flat map? That seems tricky.
It is, but we have some clever tools. This is where topographic maps come in, as detailed in box F.1. These maps use contour lines.
Contour lines, those squiggly lines.
Exactly. They're imaginary lines connecting points of equal elevation. So if you were to walk along a contour line, you'd stay at the exact same altitude. Imagine walking along a perfectly level trail that circles a hill.
Okay, I think I can picture that.
And the contour interval is the vertical distance and elevation between two adjacent lines. What's really useful is that the spacing tells you about the slope.
How so?
Contour lines that are very close together indicate a steep slope, while lines that are far apart mean a gentle slope.
Ah, so if you're looking at a hiking map and sea lines packed together,
Yep, you know you're in for a steep climb.
right, I remember seeing that. And then there are other ways to visualize this, like shaded relief maps. They look more 3D.
Exactly. They use shadows to create that three-dimensional impression, making hills and valleys really pop out visually. Figure F.2a shows a great example of how this reveals the texture of Europe.
Cool.
And with modern technology, we have what are called digital elevation models, or DEMs.
DEMs.
Yeah, these use radar data, often from satellites, to create incredibly detailed digital data sets of elevation.
So computers can draw the maps.
Pretty much. Computers can analyze this data to generate shaded, color-coded images, like in figure F.2b and c. They can even be tilted to give us those impressive oblique views. The detail is amazing.
And moving beyond just showing the surface elevation, we also have topographic profiles and geologic cross-sections, right? What's the difference there?
Good question. A topographic profile, like in figure BXF.1c from box F.1, is essentially a side view. Imagine taking a vertical slice through the ground surface. It shows the shape of the land from the side.
Like cutting a cake and looking at the edge.
Exactly. Now, if we take that profile and add information about the types of rocks and the geological structures beneath the surface, then it becomes a geologic cross-section, like in figure BXF.1d.
So you see what's underground, too.
Right. And what's fascinating is that sometimes just by observing the shape of a landform, say, a flat-topped mesa geologists can start to infer the underlying geology, figuring out which rock layers are tough and resistant versus which are easily eroded.
That's like being able to read the hidden story beneath our feet. Now, all of this uplift and subsidence leads to what's called relief. Can you explain that concept?
Sure. Relief, in simple terms, as shown in figure F.3a, is just the difference in elevation between two specific points in a landscape.
High points and low points.
Basically, yeah. We talk about high relief when there are significant elevation differences. You think of dramatic peaks and deep valleys like the Alps or the Alaskan Range in figure F.3b.
Very rugged.
Very. Conversely, low relief describes areas where the elevation differences are small, like the relatively flat plains of Kansas, maybe similar to figure F.3c.
So high relief means bumpy. Low relief means flatter.
You got it.
And it seems like this difference in elevation, this relief, acts as a kind of starting gun for a whole chain reaction of other processes that actively shape the land.
Precisely. That's a great way to put it. Once relief exists, gravity immediately starts to exert its influence. Rock near the surface weakens over time due to weathering.
Breaking down.
Right. And on slopes created by relief, this loose material becomes susceptible to downslope movement. That's the various ways that rock and soil tumble and slide from higher to lower elevations. Gravity just pulls it down.
Landslides and stuff.
Yep, landslides, rock falls, soil creep. Then we have erosion, driven by moving water in rivers, by glaciers, and by wind. These agents actively grind away and remove the surface material.
Carrying it away.
And finally, wherever these transporting agents slow down, deposition occurs, the accumulation of the eroded material, building up new landforms.
So it's this constant cycle of stuff moving from high places to low places.
That's the essence of it, yeah. A redistribution of material.
So what's the fundamental energy driving this entire process of landscape evolution? It can't just be gravity, can it?
Not at all. Good point. There are three primary sources of energy at play. First, internal energy, the heat coming from inside the Earth.
Earth's own heat engine.
Exactly. This heat keeps the asthenosphere, that layer beneath the rigid plates, hot and plastic enough for the plates to move and mantle plumes to rise. That drives the uplift and subsidence.
Okay, internal heat. What else?
Second, there's external energy, which comes straight from the sun. Solar radiation warms our atmosphere and oceans, fueling weather patterns, ocean currents, all that surface activity.
Same power. Got it.
And finally, there's gravitational energy. That constant downward pull affects everything. Gravity, working together with solar energy, drives the movement of water and air, creating winds and waves, which are major agents of erosion and transport.
So it's internal heat, solar energy, and gravity all working together.
That's the trio.
So it's like a never-ending balancing act, then, between these internal tectonic forces that are building up the landscape.
Yep, creating relief.
And the external surface processes, fueled by sun and gravity, that are constantly trying to wear it down.
Exactly. We can think of landscape evolution as this continuous battle between tectonic processes, plate collisions, volcanoes rifting, that create relief through uplift and subsidence,
The builders.
and surface processes, landslides, rivers, glaciers, wind that work to reduce that relief by moving material around.
The destroyers, or maybe recyclers.
Recyclers is a good way to put it. Destroying relief, building new depositional forms.
So if the rate of uplift is faster than the rate of erosion, the land generally rises over time. And if subsidence outpaces deposition, the land tends to sink. But without both sets of processes operating, Earth would either be a completely featureless plain, or these dramatic tectonic features would just stand unchanged forever.
That's a pretty powerful idea.
It really is. It highlights how dynamic our planet actually is. And while these changes might seem incredibly slow on a human timescale,
Like watching paint dry, maybe?
sometimes even slower, but over the vastness of geological time, even seemingly tiny annual changes can lead to enormous cumulative effects.
How fast are we talking?
Well, our sources point out that during a big earthquake, the ground can shift maybe 3 meters pretty quickly. And single intense events like major flood or hurricanes can erode or deposit meters of material almost instantly. Figure F.4b shows that hurricane damage quite dramatically.
Wow, okay, so sometimes it's fast.
Sometimes. But then we also have these long-term average rates of uplift, subsidence, erosion, and deposition.
Yeah.
These are typically tiny fractions of a millimeter to maybe a few millimeters per year, like those uplifted beach terraces in figure F.4a show. Millimeters per year, that's nothing.
It sounds like nothing, but think about it. Over millions of years, a rate of just 0.5 millimeter per year adds up. Over 10 million years. That's a 5-kilometer vertical change.
Wow. Okay, yeah. That really gives you a sense of the immense time scales we're talking about in geology. Okay, so we understand the forces at play. Now, what are the key factors that actually determine the specific kinds of landforms that we see developing around the world? Why a canyon here and dunes there?
Right, that's the next crucial piece of the puzzle. We've talked about erosional landforms carved out by water, ice, wind,
Things taken away.
and depositional landforms built up from accumulated sediment.
Things added.
Exactly. The specific shapes and characteristics of these landforms are influenced by a number of interacting factors.
Okay, what are the big ones? Our sources outline several. First, the eroding and transporting agents themselves, water, ice, and wind.
Yeah, that's fundamental.
It makes sense that a powerful river carving a deep valley will create something very different from a massive glacier grinding down a mountainside or wind sculpting sand dunes.
Absolutely. Their physical properties, how they carve, what they can carry, are totally different. And the text emphasizes that globally, flowing water is really the dominant player in erosion.
King water.
You could say that. Then there's relief, that difference in elevation we discussed.
How does relief affect the specific shape?
Well, steeper slopes, resulting from higher relief, generally mean faster movement of water or ice.
More energy?
More energy, yeah. And a greater likelihood of gravity pulling sediment downhill, quickly landslides, etc. So relief influences the intensity of the processes.
Okay. Climate is another really important factor, isn't it? Temperature, wind, rainfall.
Hugely important. Climate essentially dictates which agent, water, ice, or wind, is going to be the main sculptor in a particular region.
So deserts get wind features, polar regions get ice features.
Generally, yes. And climate also profoundly affects weathering, how rocks break down in the first place. Chemical weathering is much faster in warm, wet climates, for example.
Makes sense. Different climates, different processes, different landforms.
Exactly. Then we have the composition of the substrate, what the ground itself is actually made of.
The rocks and soil.
Exactly. Hard, resistant rocks like granite tend to form steep cliffs and rugged terrain because they resist erosion.
About Yosemite.
Perfect example. Whereas softer stuff like shale or loosely packed sediment erodes much more easily, typically resulting in gentler slopes and more rounded features.
So the material matters a lot.
A whole lot.
And it's not just the non-living environment, is it? Life plays a role too.
Definitely. Biological activity is a significant factor. Organisms can weaken the ground, think burrowing animals loosening soil, or plant roots chemically weathering rock.
Breaking things down.
But they can also strengthen it. Like the extensive root systems of forests can bind soil together, making it more resistant to erosion.
Interesting. So life cuts both ways.
It does. And finally, we have the factor of time. Landscapes aren't static snapshots. They evolve continuously.
Right.
A brand new gully carved by a flash flood looks very different from a mature, deep canyon that the same river might carve over millions of years. Time allows these processes to really work their magic.
It's really incredible to think about how all of these interconnected factors The agent, relief, climate, material, life, time are constantly interacting.
It's a complex dance.
And speaking of factors influencing landscapes, our sources also highlight the increasingly significant impact of, well, us. Human activities. We're not just passive observers anymore, are we?
Far from it. You could argue humans are now one of the most powerful geological agents on the planet.
Really? How so?
Well, think about it. Consider the vast open-pit mines that literally remove mountains, or the artificial hills created by mine tailings and landfills that fill valleys. Figure F.5 shows some examples like pyramids and highway cuts.
Yeah, we move a lot of earth for construction and mining.
A staggering amount. We engineer slopes for highways and railways, build massive dams creating huge lakes, fundamentally altering river systems.
And coastlines too, right? With seawalls and jetties.
Absolutely. We've altered coastlines, changed river courses through channelization, created those enormous reservoirs. The scale is just immense.
It truly is.
And even seemingly smaller scale activities add up. Urbanization, all that pavement and buildings means rainwater can't soak in.
So it runs off faster,
Yeah.
causing floods.
Exactly. Increased runoff, higher peak flows in streams. And in rural areas, agriculture, especially removing natural vegetation, can dramatically increase soil erosion. The statistic mentioned in the text is pretty mind-blowing.
Yeah.
The total area of paved and built-upon land in the U.S. now exceeds the entire area of the state of Ohio.
Wow. More than Ohio. That's hard to even picture. That really drives home our footprint.
It certainly does.
Okay, so we've explored the fundamental forces, the key factors, including us. Now, let's delve into one of the most critical players in this whole dynamic process, water, and its continuous journey, the hydrologic cycle.
Absolutely. As we've kind of hinted at all along, water in all its forms, liquid, gas, solid ice, is an incredibly powerful agent of both erosion and deposition. Figure F.6 gives a nice little snapshot of that with the pond, seepage, evaporation.
And Earth has a lot of water stored in different places.
Tons of it, stored in various reservoirs as detailed in Table F.2. The vast majority is in the oceans, obviously, but also significant amounts in glacial ice, groundwater beneath the surface, lakes, soil moisture, even locked up in living organisms, the atmosphere, and of course, rivers.
And all of this water everywhere is the hydrosphere.
That's the term, yes. All the water in all those reservoirs.
And the hydrologic cycle is how it moves between them.
Precisely. The hydrologic cycle is the continuous dynamic movement of water between all these different reservoirs. The geology at a glance spread in our source gives a fantastic visual overview.
It's like a giant plumbing system for the planet.
That's one way to think about it. Driven mainly by solar energy and gravity, it's a never-ending process. That Longfellow quote mentioned captures the poetry of it, this constant transformation.
And without this cycle,
the erosive power of rivers and glaciers just wouldn't exist. They'd run dry or melt once and be gone. The cycle keeps replenishing them.
Okay, so let's walk through the main stages. It starts with evaporation, right? Sun heats water.
Yep. Solar energy heats liquid water, mostly from the oceans. The source says something like 417,000 cubic kilometers a year evaporates.
That's a huge number.
It is. Turns it into water vapor, which rises into the atmosphere.
Then it cools down up there.
Right. As the vapor rises, it cools and undergoes condensation, changing back into tiny liquid droplets or ice crystals. That's how clouds form.
Okay, clouds, then precipitation.
Exactly. When those droplets or crystals get big and heavy enough, they fall back to Earth as precipitation, rain, snow, sleet, hail. Most of it, about 3/4, falls right back into the oceans.
But the rest falls on land. And what happens then? It doesn't just sit there?
No, it follows several paths. Some gets temporarily stored in soil or taken up by plants and animals. That water eventually returns to the atmosphere through evapotranspiration.
What?
Evapotranspiration. It's a combo of evaporation from surfaces like puddles or lakes and transpiration, which is water vapor released by plants and animals.
Ah, plants breathing out water vapor.
Yeah, sort of, yeah. Then some precipitation flows over the land as surface runoff into streams, rivers, lakes, and eventually back to the sea.
The obvious path.
Right. In cold places, snow can accumulate and become trapped in glaciers for long periods, and a significant amount infiltrates the ground.
Soaks in.
Yep, seeps down through soil and rock to become groundwater, stored below the surface.
And that groundwater moves too.
It does, though usually much slower than surface water. It flows underground and eventually might emerge at the surface in springs, feeding rivers, or it might flow directly into the ocean underwater.
It all connects back.
It's all interconnected within this vast global system. Even the water in living things gets cycled back eventually.
Our sources also mention residence time. What's that about?
Residence time, as shown in Table F.3, is the average length of time a water molecule hangs out in a particular reservoir.
How long it stays put?
Pretty much. And it varies wildly. A water molecule might only be in the atmosphere for hours or days, maybe weeks in a river.
Pretty quick turnover.
Very. But in the deep ocean, or locked in an ice cap, or deep groundwater, it could stay there for thousands, even hundreds of thousands of years.
Wow. So the water in your tap could be really, really old, geologically speaking.
It certainly could have spent a long time in a different reservoir before getting cycled through.
It's a fascinating thought. Okay, so Earth has these incredibly dynamic water-shaped landscapes.
Yeah.
How does this compare to what we see on other planets and moons in our solar system? Are they all this active?
That's an excellent question, and section F.5 really highlights the contrast. Most other rocky bodies are far more static than Earth. Each has its own unique history, sure, but generally much less active tectonics and erosion, especially currently.
Let's start close by with the moon. The description is static, pockmark. Sounds pretty dead geologically. Figures F.7a and B show all those craters.
That's a fair description. It's largely shaped by ancient meteorite impacts and some early volcanism. Crucially, it lacks plate tectonics, no new mountains or volcanoes being built.
And no water or air to speak of.
Right. No real atmosphere, no liquid water, so no hydrologic cycle. That means no significant erosion by rivers, glaciers, or wind. The surface we see is billions of years old, largely unchanged.
Just sits there getting bombarded.
Pretty much. You basically have the older, heavily cratered highlands, which are lighter colored, and the younger, darker Maria, those vast plains of basalt lava, probably from huge impacts long ago.
Okay, moon. Old, static, cratered. What about Mars? The red planet seems more interesting. It has a thin atmosphere, right? Dust storms.
It does, yeah. Unlike the moon, it has an atmosphere, thin as it is, enough for those planet-wide dust storms. And the really intriguing part is the evidence for past liquid water. Box F.2 and figure BXF.2 show those channels.
Channels that look like rivers.
They really do. They're strong evidence channels, scour marks, gullies, sediment deposits suggesting liquid water flowed on Mars long ago. We don't see stable liquid water today because the low pressure makes it evaporate almost instantly.
But it was there.
The geological evidence is pretty compelling. Spacecraft have found subsurface hydrogen, minerals like hematite and gypsum that form in water, and rovers have seen layered sediments that look water-laid.
So a wetter, maybe warmer Mars in the past? That's huge.
It's a major area of research. The big questions are, how much water was there? Where did it go? Could life have existed?
Where is the water now?
The leading idea is that as Mars lost its atmosphere, the water evaporated, and what's left is mostly frozen underground or in the polar ice caps.
So Mars had water action, but it stopped.
Largely, yes. It also lacks Earth-style plate tectonics, so no big mountain ranges from collisions. But it does have massive relief from other processes, things like the Tharsis Ridge Bulge, the Valles Marineris Canyon, and huge volcanoes like Olympus Mons, shown in figure F.7c, biggest volcano in the solar system.
Wow. So some volcanism in past water, but mostly old features now.
Except for wind erosion and deposition, yes, most major features are billions of years old.
Okay. And Venus, Earth's sister planet. Is it like Earth?
Similar size, but a very different place. Its surface seems to have been almost entirely resurfaced by volcanism relatively recently. Geologically speaking, maybe 300 million to 1.6 billion years ago. Much younger than the moon or Mars surfaces.
Resurfaced by volcanoes.
Yeah, its thick atmosphere protects it from small impacts, so fewer craters. Radar images, like figure F.7d, show volcanoes everywhere, shield volcanoes, lava flows, calderas. There's evidence of rifting, too.
But no water.
Definitely no liquid water. The surface temperature is scorching hot, hot enough to melt lead, so no hydrologic cycle.
And the thick atmosphere, does it cause erosion?
You'd think so, but the winds near the surface are actually pretty slow, so there's limited erosion or deposition. Those volcanic landforms are largely preserved as they formed.
So Venus, hot, volcanic, but also relatively static in terms of surface changes now.
That seems to be the picture, yeah.
And the sources briefly mention other places too, like icy moons.
Right, just to show the diversity. Enceladus, a moon of Saturn, is icy and cracked, with geysers erupting. Figure F.8a. Io, orbiting Jupiter, is incredibly volcanically active. Figure F.8b. And even distant Pluto surprised us with rugged mountains and icy plains. figure F.8c.
It really shows that landscape means very different things across the solar system.
Absolutely. Each world tells a unique story of its internal and external processes.
Well, this has been an exceptionally comprehensive deep dive into the constantly evolving landscapes of our own planet and beyond. We've really covered a tremendous amount of ground,
We certainly have.
from the fundamental forces of uplift and subsidence, erosion and deposition, to the absolutely crucial role played by the hydrologic cycle.
And how that compares to the moon, Mars, Venus, and elsewhere.
We've thoroughly explored the core geological concepts, the key processes.
How we map topography using contours, DEMs, profiles, cross-sections.
Looked at examples like those geotours references, the factors controlling landforms, agent, relief, climate, substrate, life, time.
And of course, the increasing human impact, plus the whole hydrologic cycle, breakdown, reservoirs, processes, residence times. I think we've hit everything in this chapter.
Yeah, it feels like we've covered the geology ideas, the processes, the diagrams, the examples, the whole 9 yards. Our mission to understand landscape development, the hydrologic cycle, and compare with other worlds is definitely complete.
Agreed.
So hopefully you, our listener, will now maybe look at the landscapes around you, whether it's a familiar park, a winding river, maybe even just your backyard, with a newfound appreciation for the immense geological forces that have shaped them.
Yeah, the forces acting over vast stretches of time and still acting today.
Exactly. And to leave you with one final thought-provoking question. Consider a specific landscape that you know well, maybe a local mountain range, a stretch of coastline you visited, or even a particular valley. Based on what we've discussed, what dominant geological processes do you now think have been most influential in shaping its current form?
And perhaps, how might that landscape potentially evolve in the distant future as these processes continue their slow, relentless work? Something to ponder.